Good morning to everyone. So in this presentation, I'm going to present some experimental results on fatigue damage in the 360L steel produced by laser power bed fusion, which is a quite common additive manufacturing technique for metals. So this is a joint collaboration between the University of Udine and the Institute of Physics of Material in Brno. So in the past decades, many studies focused on the role of the so-called persistent slip bands and persistent slip marks in fatigue damage. So basically, the persistent slip bands are region of material where strain localized during cyclic loading. And when these bands intersect the free surface of the material, they create the extrusion and sometimes also intrusion, which then appear as marks on the free surface. And the intrusion are related to crack initiation sometimes. However, these studies focused on, let's say, conventional material or wrought metals, and not on the additively manufactured ones. And the difference between the two is significant. For example, in the case of the 360L steel, the wrought material presents a low dislocation density and no dislocation structure in the initial condition. On the contrary, the additively manufactured material presents a high initial dislocation density and also a dislocation cell structure. Of course, this different microstructure leads to a different cyclic elastoplastic response in terms of cyclic hardening and cyclic softening, and it also has an influence on the yield strength of the material. So for this reason, we decided to investigate the role of persistent slip bands and persistent slip marks, even in the case of the additively manufactured materials. So in this work, we decided to focus on, let's say, relatively small strain amplitude of 0.4%. Here I reported the cyclic stress response of the material, which consists in 3 stages. In this work, we decided to focus on the first part of the second stage, which is the cyclic softening. So basically what we did is we performed some low cycle fatigue tests, which were interrupted at different number of cycles. And then we performed some microstructural observation on the surface and also on the interior material. Okay, so this is the outline of my presentation. I'm going to briefly explain the methods and then I'm going to show the experimental observation. So concerning the material, we fabricated some cylinders in the vertical direction using, as I said, laser power bed fusion and the 360L steel. Then these cylinders underwent a stress relief heat treatment, and then they were machined to the specimen geometry. In addition to the cylindrical specimen, we also fabricated some flat specimen using EDM from the head grip of the cylindrical ones, and the surface of this flat specimen was also electropolished. These specimens were used to investigate the persistent slip marks during cyclic loading. Of course, both the flat and cylindrical specimen were then tested in strain control at 0.4% of strain amplitude. And as I said at the beginning, the tests were stopped at preset number of cycles up to 4,000. Then we observed the surface of the flat specimen, at first using optical microscopy and then using SEM. And then we also extracted some samples from the cylindrical specimen, which were then analyzed by SEM and TEM analysis. Okay, so before I'm going to present the microstructural observation, I would like just to show the cyclic elastoplastic response during this low cycle fatigue test. So as you can see here, both the type of specimen exhibit cyclic hardening for the first 5 cycles and then cyclic softening, as expected. As you can see, there is also a slightly lower stress value for the flat specimen, and also elastic modulus, which is not visible here. And this is due to, let's say, a high ratio between porosity and cross-section area of the flat specimen. In addition to that, we also observe a slightly higher hardness on a surface layer of the cylindrical specimen due to the machining, and this could also have an influence on the mechanical response. Okay, so concerning the microstructural observation, we started by observing the surface of the flat specimen using optical microscopy. So as you can see here, just after 5 cycles, some slip steps are present on the surface of the specimen. And with increasing the number of cycles, the slip steps becomes more evident, and also the quantity increases. However, using optical microscopy is difficult to describe the morphology of these slip steps. So we perform also SEM analysis on the same surfaces. So here it's not so easy to see, but there are some slip marks on the surface with different inclination and with respect to the loading direction. And this different inclination is due to the, it's likely due to the different grain orientation from region to region of material. And of course, these slip marks, in this case are marks, are more visible after 4,000 cycles. And at higher magnification is also possible to find some, let's say, morphological features of these slip marks. As you can see on the left figure, there are some extrusion. We can say that these are extrusion because they are a brighter strip of material, because they protrude from the surface. And close to some extrusion, there are also some intrusion. In this case, the material appears darker compared to the surrounding material because, let's say, the material entered the surface. These kind of intrusion are, as I said at the beginning, related to crack nucleation. So in this case, we measure the surface length of some of these intrusion, because using ECM is impossible to measure the depth of the intrusion. So here I reported the value. The surface length range from 20 to 40 microns with increasing the number of cycles. However, at the same time, we also observe some surface crack, which start from surface pores. And again, here we measure only the surface length of this crack. And as you can see here, the surface length is definitely higher than the one of the intrusion. And it ranges from 35 to 210 microns. So we can say that for the additively manufactured materials, the crack starting from surface pores is a more detrimental damaging mechanism. Okay, so these persistent slip marks that were observed on the surface of the material, as I said at the beginning, are related to the bends within the bulk material, so in the interior material. So at this point, we decided to investigate also the interior of the material, in this case of the cylindrical specimen. So we extracted some samples and we perform ECM analysis. And as you can see also in the interior of the material, there is the presence of some bends with different inclination. And in this case, we were also able to observe that some of the bends can overcome the so-called melt pool boundaries, which does not represent an effective barrier to slip localization. Yeah. Of course, with increasing the number of cycles, in this case, the bends becomes more wider, let's say. At this point, we also performed some TEM analysis, once again to describe, in this case, the dislocation arrangement within the bends. So using TM, we were able also to identify the bends And as you can see, maybe here is better, the bands are characterized by a low dislocation density compared to the surrounding material. And they are also characterized by a kind of ladder-like dislocation pattern. And this is similar to the conventional FCC metals. However, in this case, the walls of the ladder-like pattern resemble the underlying or the surrounding material cell structure, which is characterized by the initial cell structure. The initial cell structure, on the opposite, compared to the bands, remains almost stable during cyclic loading. And this was confirmed also by other TEM analysis, TEM images, which were acquired on different, let's say, crystallographic planes. So as you can see, after 200 and 3000 cycles, the cell structure remains almost stable. Okay, so with that, I conclude my presentation with just a summary. So we can say that slip steps are present on the specimen surface just after 5 cycles. Of course, with increasing the number of cycles, the slip activity increases within the bands, and this creates also extrusion, intrusion on the surface of the specimen. The intrusion can promote crack initiation. However, surface pores trigger early crack nucleation. And then using TM, we were also able to describe, let's say, the dislocation arrangement within the bands, which are characterized by a low dislocation density and a ladder-like dislocation structure, which resembles the underlying cell structure, which appears to be stable during cyclic loading. Thank you for your attention.